All right, no audio for that one.
Captions on.
Now we're back. I'm not doing that. This is a luxury. We've got like years of videos. You just go back to the last one. So in the Henry's Law application, really what we're looking at is a sort of, we're just adopting a similar form to the standard activity coefficient model. But in this case here, it's not sort of the ideal versus non-ideal, it's just sort of a correction term. So the counterintuitive nature here is that for a standard activity coefficient, as x of I goes to 1, the activity coefficient goes to 1. In the case of this Henry's Law correction, it's a little bit opposite, right? So I just want to highlight that this is not the same thing as a standard activity coefficient. It is not necessarily directly related to the excess Gibbs energy. That's why we put a little star right there just to show that this is a strictly empirical approach that is useful for tabulating data that people have measured experimentally. Now, on to vapor-liquid equilibrium. So, you're on an exam, and you see a question that says vapor-liquid equilibrium. What is your starting point?
Draw a picture.
So just humor me, guys. I heard a muffled one.
Equal partial.
Partial fugacities of the liquid equal to the partial fugacity of the vapor. All right. Let's list all of the assumptions necessary. Let's think of as many assumptions as we can. So break it up into as small steps as possible. How do we get from this governing equation to Raoult's law? Let's list our assumptions. Go one by one. As granular, small assumptions as we can get.
Ideal gas.
Ideal gas, okay. Let's say it's ideal pure gas. What does that allow us to do mathematically if we assume that it's an ideal pure gas?
Fugacity of the vapor equal to partial is y multiplied the pressure.
So that's two assumptions actually. That's ideal pure gas and a different assumption. So what is it? Only assuming that we have an ideal pure gas. What does that allow us to do?
Fugacity in the pressure.
That the fugacity of the pure fluid as a function of temperature and pressure is simply equal to the system pressure. What's another assumption? I have a handout here.
Partial fugacity equal the molar y multiplied by the fugacity.
So what is the assumption though that's built in there? The physical mechanism that we're assuming is happening in these fluid mixtures. So we have gone over all of these assumptions in our notes. Let's focus on the vapor phase. Okay, so we've talked about the pure fluid. What about the mixture? Ideal mixture in which phase? So we have ideal vapor phase mixture. So I'm not letting you off the hook. What does that mean mathematically?
It's linear. You can add everything together, weighted by its mole fraction, right?
So is there some way that you could relate one of these variables to one of these variables with this assumption?
Yeah. Partial fugacity of ion vapor is yi times p, right?
Yes, you're combining two, but I want to
Yeah.
go as slowly as possible.
Okay, times the fugacity of I, the T and P. Yeah.
So if you assume it's a pure ideal gas fluid that allows us to write the fugacity of the vapor of the pure material as its pressure, then we can assume that they mix in an ideal mixture, which allows us to write that the partial fugacity is a weighted value of the mole fraction times by the pure fluid fugacity. You don't have to use both of these assumptions. If you say it's an ideal gas, then you will put these together and that the partial fugacity in the vapor gas and mixture. So that solves the vapor phase, right? We have gone to Raoult's law. We have taken partial fugacity of species I in the vapor phase, and we've turned it directly into Raoult's law. Now remember, we have this equation for every single component system. Liquid phase. What are some assumptions?
Density of the liquid equals the saturation of your gas.
Right, that's a mathematical substitution. What is the physical meaning of that?
Because the fugacity of the liquid does not change a lot as we change the pressure.
So what you're saying is that the
Fugacity of the liquid
fugacity of the pure liquid, right,
at any temperature
is equal to the
saturation. Fugacity of saturation.
fugacity, oh, the saturated fugacity of the vapor? That's what you're saying? Is that the assumption? Smallest steps as possible. Baby, baby, baby steps. So physically, what are some assumptions? Think about it in terms of temperature, pressure, and mixtures. Everyone uses Raoult's law. Everyone knows Raoult's law. The whole point of sort of, real thermodynamics is Raoult's law is not good. Raoult's law is very bad. So I want you to know why it's bad. Baby, baby, baby steps. We can sit here all day. We're going to go over this material. There's no getting out of it.
Ideal liquid mixture.
Ideal liquid mixture, excellent. That's one. What is the assumption there?
Like the one above, but instead of vapor with liquid, the partial fugacity is linear. So I don't weighted more fraction, like someone said.
Yes. Partial fugacity of the liquid, which is a function of temperature, pressure, and liquid phase composition, is simply going to be equal to the mole fraction times by the partial fugacity of the liquid, which is a function of temperature and pressure. And the consequence here is that the activity coefficient is equal to 1. We are missing 2 assumptions. If I had brought candy bars, would that have sweetened the deal here?
Yes.
No pun intended. We have 2 assumptions left. Right? We have here the fugacity of the liquid at temperature and pressure that is not equal to Psat. Notice that there are 2 things different. This is an F. That is a P. This is an L. That is a saturation. How do we change those 2 out?
So do we have to assume that the pure component fugacity in the liquid phase is equal to the fugacity at saturation in the vapor phase?
Exactly. Now, under what circumstances would that be true?
Low pressure.
Low pressure. Exactly. That's right. That's very good. In this case, that means we can write that the fugacity of species I in the liquid as a function of temperature and pressure is equal to the fugacity of, the pure fugacity at saturation. So which correction have we neglected in this assumption? Pointing factor is gone. So pointing correction is 1. There's no pointing correction. Now the last one's a little bit hidden in other things. We can basically just say that I'm writing ideal vapor phase twice because that allows us to write that the fugacity of pure species in the liquid as a function of temperature and pressure is equal to, actually no, that's not the right way to write it. I'm trying to break this down into small steps as possible so we can highlight every single assumption. In this case, we are then writing that the saturated fugacity of the liquid is simply equal to the saturation pressure. And here we have Raoult's law.
So that's kind of like the first assumption.
It is, yes. It's a consequence. If you assume ideal gas in the vapor phase, then that means that this is true, this is true, and this is true. But where's the fun in that? Right. So we put this all together and we have derived Raoult's law. So today what we're going to do is we're going to focus on Raoult's law. How we can use it to solve problems. Because it gets only more complicated beyond that. All right. So, let's see, I covered a lot of that, but so let's talk about bubble and dew curves. So I have in the handout here a TXY diagram and a PXY diagram. Let's go over very quickly how we read them again. And the procedure that I'd like to go over is going to hold true, right, for any type of phase diagram. Because when it comes to an exam, I'm going to give you as wacky a phase diagrams as I possibly come up with the hope that you've never seen it before. Right? That's going to be my objective. Oh, here's one. I got extras. I have one buried in my notes somewhere. Because I want to break down sort of how we can read phase diagrams. And so let's see. So you have the TXY and PXY diagrams. You have isopropanol and propanol and methanol and 1-pentanol. So let's first look at the TXY diagram. Let's go over it again. Now, you'll notice that in the TXY diagram, I have Z of isopropyl alcohol. Right? That's going to be the more volatile species compared to 1-propanol. Just a little bit, not much. Okay? So what that means is that isopropyl alcohol boils at a lower temperature for the pressure that the TXY diagram is constructed at. So in this case, P is constant. So we're changing the temperature and composition, but holding the pressure constant. In this case here, I believe it's just 1 atmosphere. It says it right there on the chart. So isopropyl alcohol boils at 82.2 degrees Celsius. And 1-propanol boils at 97.2 degrees Celsius. So I have 2 lines. Now, in sort of the sheltered world of the classroom, we make it very clear which is the bubble point and which is the dew point, because we're helping you along. In the real, harsh world of reality, if you go to Fluid Phase Equilibria, which is a reputable, good journal, and you look at phase diagrams, They do not tell you. They don't define what the chemical potential is. They don't tell you which one's the bubble point, which one's the dew point. They expect you to understand and read phase diagrams. Okay? So looking at this chart right here, let's erase everything. Let's erase TXY, let's erase temperature, let's erase this, let's erase that. Where's the two-phase region?
Inside the tubes.
Yeah, inside the curves. Because when you get to liquid-liquid equilibrium, vapor-liquid-liquid equilibrium, solid liquid-liquid equilibrium, you will have boatloads of lines. And they will all be differentiating different phases. Some will be vapor-liquid, some will be solid-liquid. They want to make as much data onto one chart as possible by slapping on as many confusing lines as possible. How do we know that we're in two-phase regions? Because if I draw a line at constant temperature, which is one of the three governing criteria that have to be met for phase equilibrium, my whole chart is drawn at constant pressure. So if I have constant pressure and constant temperature and I'm crossing multiple lines, you know you must be in a two-phase region because there are multiple solutions to the composition. Any phase diagram, this is going to hold true. Now, we're going to break it down. So we know we're in a one-phase region here because I could draw a line below the two-phase envelope and never encounter anything, meaning that the two fluids would have to be infinitely miscible. Same thing up here, in the vapor phase, the two fluids would be infinitely miscible above a certain point for the vapor phase. Low temperatures, I am, which phase?
Liquid.
Liquid. High temperatures?
Vapor.
Vapor, there we go. So if I'm at this particular temperature of the system, this particular composition, I'm in the two-phase region. Where my line intersects the bubble curve, that corresponds to the mole fraction in the liquid phase of the species that we have constructed this diagram for. Where my line intersects the dew curve, that corresponds to the mole fraction of the vapor phase. Changing the composition between these 2 points does not affect anything in thermodynamics. It only affects the mole balance. It only affects whether or not I have more of the liquid phase or more of the vapor phase. You have to convince yourself this is true. Thermodynamics only cares about the temperature and pressure for the phase equilibrium. The total amount of the phases determines that. Now the PXY diagram conveys exactly the same information. However, it's much easier to calculate. So in this case here, we have the mole fraction of methanol in a methanol-pentanol mixture. I have 2 lines. Not quite exactly as I drew it on there, but what is this point right here? Can someone physically describe what it represents?
You're to stay at the same temperature, that's the pressure, where the volatile, or one of the boils. Yeah, where the,
It's the vapor pressure of pure, whatever the other one is.
Yes, this is the vapor pressure of pure 1-pentanol. So this is P vaporization of 1-pentanol, 1P, I'll try that, at the temperature that this diagram is constructed at. We know it's the less volatile species because it has the lowest saturation pressure. Question.
How would you physically define the vapor pressure?
How do we physically define vapor pressure? The vapor pressure is the position where you have vapor and liquid in equilibrium. So if we were to look at a PT phase diagram for a pure fluid, we have a line that separates liquid from vapor. At a given temperature, we have a pressure where the vapor and liquid phases are in equilibrium of a pure mixture. So in this case here, the PXY diagram is 1 point on this line right here. Now, for a pure fluid, the region between vapor and liquid is a single line. For a mixture, it separates, and that's why we have a bubble point and a dew point. So in a pure fluid, the bubble and the dew point are identical. So up here, this is the saturation pressure at the temperature for methanol. It is the more volatile species because it has the higher saturation pressure. So at a higher system pressure, the methanol will boil away. At low pressure, regardless of the temperature, what phase am I going to be in?
Low pressure, you said?
Low pressure.
Vapor.
Vapor. High pressures? Liquids. What is this line?
Ooh, wait, you, that's,
Wait,
you
yeah.
gotta-
Oh, whoops. Oh, sorry. Liquid, vapor, sorry. This line,
The bubble.
bubble, and this line, dew. Okay, I'm at this system pressure, I draw it across. How do I figure out what is my liquid composition?
You didn't know the composition.
Where do I figure out my liquid composition?
Bubble.
Bubble, so this corresponds to the mole fraction of the liquid phase. Where's my vapor? And that's it. Now let's say, for example, I were to give you a liquid-liquid phase equilibrium drawing. Oftentimes they look like this. Let's say it's a TXY diagram for liquid-liquid equilibrium. It would look like that. Where's the two-phase region? At high temperatures, for this particular fluid mixture, they're miscible above something called the upper consolate temperature. Upper consolate temperature. We can go over this again later, but if I wanted to figure out what's the composition of my two phases, I draw a line across here. This would be the composition of component I in phase 1. This would be the composition of component I in phase 2. What if I were to draw a solid liquid equilibrium phase diagram, a liquid-liquid vapor equilibrium phase diagram? Same procedure. Draw a horizontal line because the temperatures have to be constant across each phase. The pressure generally is going to be held constant across all these ones. Phase diagrams, done, right? So what we're going to do is we're going to go over very quickly all of the governing equations for vapor-liquid equilibrium for an ideal system, meaning that we have an ideal liquid phase and an ideal vapor phase, which gets us to Raoult's law. And then this is audience participation day. I'm going to have you all derive the equations. So here's what we are left with. For a Raoult's law vapor-liquid system, we have that the total composition is equal to 1. We have the liquid composition is equal to 1. Sorry, vapor, we have the liquid composition is equal to 1. These are consistency relationships. These are mass consistency relationships. Thermodynamic consistency relationships is the Gibbs-Duhem equation. And we have our phase equilibrium. Now for the saturation pressure, oftentimes you will write it with Anton's equation. I think that's right. I can't remember if I got these switched or not.
I think it's T minus C. I think it's right. I think it's right.
I think that's, if not, it's close enough. It's an exponential form. The numbers could be positive or negative. Okay, so first let's define what the bubble and the dew point are. So in a piston cylinder device, in the bubble point, we have an all-liquid system, and we are slowly depressurizing it, or we're slowly heating it. PXY diagrams are always easier to generate, because temperature has an exponential relationship with the saturation pressure. So even for a Raoult's law system, it's a system of nonlinear equations if you're solving for TXY diagrams. For PXY, temperature is fixed, which means vapor pressure is fixed, which means you have a system of linear equations. So even in the simplest system, vapor-liquid equilibrium, as the function of temperature, is a nonlinear system. For liquid-liquid equilibrium, it's always a nonlinear system. So in the bubble point, we have an all-liquid system, and we're looking to see at what pressure or temperature the very first bubble comes out of solution. Now this allows us to make a very important assumption. You'll notice Raoult's law does not have the total composition built into it. So by calculating the bubble point, it allows us to insert the total composition into Raoult's law. In this case, for the bubble point, the whole way that we can solve this expression is that the mole fraction in the liquid phase of every species is equal to the total system composition. This is the only assumption that we need to solve this problem. For the dew curve, it is the opposite system, where I have a vapor and I'm pressurizing it, or I have a vapor and I'm cooling it. It's exactly the same approach as the bubble point, but it's flipped around a little bit. In this case, the mole fraction of the vapor phase is equal to the total composition. That is the only thing that I need to do. So I'll give you one additional hint before I have you guys solve for the equations of the bubble and the dew curve, is that in these derivations, it's sort of counterintuitive. We want to start off with an equation where we know nothing, and then substitute in values where we know some things. So in all of these equations that I've listed right here, let's ignore Anton's equation for a second. Which equation for the bubble point do I know literally zero values of? Of all of our vapor-liquid equilibrium equations. No, I know x.
Okay, so you take the summation of
Summation of y. You rearrange and solve for y, you're done. For the dew point, which one don't I know? It's the opposite, right? Everything's the opposite. All right, here's the objective. Let's have everyone on this side of the camera solve for the bubble point curve. Everyone on that side of the camera solve for the dew curve. And one lucky volunteer gets to show the final result. And the derivation.
and not fail.
We are so confused about this.
Okay, so what are we doing? We're doing the y parentheses is choose one, which is gonna be I see, you just plug it in. Yeah, you just plug it in.
That's-
And what is the result should I stop at?
It should be an equation that is condensed, that will allow you to explicitly solve for, let's say, the pressure. Let's say we're trying to generate a PXY diagram, so we want the bubble curve of a PXY. Let's stop there. Same thing with the dew. But there is a single, clearly obvious, nice compact form. Now we're going to do this for an arbitrary number of components, not just two components. Do it for an arbitrary number. So you should have an infinite summation.
This is why we have a straight line.
I've literally been doing this for like 3 or 4 years now. Today's the day that I didn't hit.
So,
I think I did hit the button, but I think I just must have like not got it. Yeah. Who's stuck? Is anyone stuck? Raise your hand. This is a learning experience opportunity. This is not, I want you to feel bad about my solve opportunity.
I
Here we
already
go.
do.
Let's see.
So we're trying to solve for y now.
Yeah. So,
Yeah. What is y?
You're looking for
What
the
is y?
Duke curve, right? So you can't have any yi's in your expression. So you need to get this piece sat somewhere down here by with the yi's. Replace that, but that's kind of on the right lines, but we don't know what y is. This isn't an explicit equation for assumption.
so this one we wanna get temperature.
So who's confident that they've got it all worked out?
You solve for y and Bell's law. Yeah.
Actually, it's not tricky, sorry.
Yeah.
Oh, sorry, I told you, I said creator, and I got confused. You're trying to get rid of the x. This is the Duke curve.
Yeah.
What should I say to the Duke?
You said
That's the bubble
this is
curve?
the bubble.
Oh, okay, yeah, that looks more like the Duke curve.
Okay.
So yeah, so
Yeah,
that's
and so then,
the right approach, but the wrong.
because this one, the goal would be to
But that's not exactly
solve
the
this,
curve.
have a temperature, so that t equals some function of y, but you can't because t is buried in the p side. This works too, this makes sense, this works too.
Well, it's the same equation.
Yeah, yeah.
You just I just multiply by t.
Yeah. Yeah.
Okay,
Other one?
do I have a volunteer for team bubble curve? So we have a Duke curve?
We're not the bubble.
Who's bubble, who's Duke?
We were the.
We were the bubble.
You were the bubble?
We did both.
Oh, maybe.
We're not the bubble.
Oh, wait, hold on. No, I said, I don't remember which side I said.
I won.
So-
All right, play it back.
I'm okay with both.
Do I have a volunteer for the bubble curve? Okay, let's walk us through the bubble curve derivation.
Yeah.
I'd like to do it this way because the thermodynamics is done here. The actual solution to this is just algebra. Because in reality, if you are good at sort of your linear or nonlinear solutions, just dump it into a big equation solver and it's done, right? Satisfy all these at the same time. Okay, so walk us through.
Yeah. Okay, so the bubble curve we have like two summation of yi should be equal to 1, okay? So we need to define yi in terms of things we know. So we have yi is equal to, should be here, b equal xi b set I. This is a function of temperature, okay? Okay, so we can rewrite this one as yi equal xi pi set over the total pressure of the system, okay? We go back into the summation. And the summation of xi pi set over b is equal to 1, okay? We can just move the p from here, write it here, because it is fixed across all the phases. This is the p of the system. This should not be enough to solve. We have this equation, which is xi is equal to 1. So we have like I number of components. You would define one of them, one of these x's as 1 minus the other x summation. So it reduces the number of unknowns. Yeah.
Perfect.
Yeah, and it's xi, I suppose that should be equal to zi, because this is the assumption of the bubble.
That's the most important assumption is right there, that the x is equal to the z. Without that assumption, we cannot solve for the bubble curve. That is the assumption we need to have. Because if we don't know, I erased all my phase diagrams, right? But if we don't know, right, if we're in the one phase or two phase region, we have to solve everything simultaneously. So if we can assume that the total composition is equal to the liquid composition, then we know that we're on a curve that only has one solution. That's your answer. Thank you very much. And dew curve. Volunteer for the dew curve. I'm looking at Brennan to volunteer for the dew curve. Walk us through.
Okay. I could be wrong. I bet I'm wrong.
No, no.
Okay.
It's the same exact procedure, but just switch it.
Yeah. Okay, so these are the things that we know. So we make that substitution like we did before. Yeah. Exactly what Tarek said. And we're gonna solve for xi in terms of yi, so we end up with here. And then we make a substitution of this equation into this one. And we end up with and that is the curve.
Yeah. The conventional form that we usually write it in, we just flip it over, do the reciprocal of both. But that's exactly right.
Oh, I was worried about that.
No, so that's, I mean, it just depends. Like what you see most in most engineering textbooks.
Oh, okay, yeah,
They just write it that way, just so that students can be like,
I see.
here's your equation, put the numbers in, here's your result. Perfect. Thank you very much. And on an exam, they'll take 15 seconds to do on an exam, right? To remember the bubble and dew curve. Now let's say, for example, that we don't use Raoult's law, we use a modified Raoult's law. Does our approach change? Does anything change? Short answer is no, our equations are almost exactly the same. Right? So in the case of the bubble point, all I will do here is I will just write P is equal to summation. Okay, that's it. For the dew curve, it's a little bit trickier.
Yeah.
Why is the dew curve trickier? Right, let's go back to our concept here. Right, the bubble and the dew curve. So at the bubble point, we assume that everything's liquid, so our total composition is the same thing as the liquid phase composition. In the dew curve, right, so rather here we don't know what the vapor phase composition is. For the dew curve, we know the vapor phase composition, but we know nothing about the liquid phase. Does anyone see a problem with that when trying to apply this equation for a dew point calculation? Yes, Stark.
Gamma is dependent on the x that we don't know, so we have like a loop.
Exactly. So how do we solve a non-ideal liquid phase vapor liquid equilibrium problem? And it is much simpler than you may believe. So if we were to generate, and again, let's go with PXY diagram, because PXY is the simpler of the two. Again, oh, I just turned my brain off. This is my Z of component A. How should I draw this? Does Z of A, which is the more volatile species, does it have a higher or a lower vapor pressure?
Lower.
Oh, higher.
Higher.
Yeah, that's right.
So should I draw my curves going up
Can't
or
do
down? Where should I put this vapor pressure for pure component A? It should be higher up, right?
Oh, yeah, okay.
For component B, it should be lower down. Now, if we were to look at our bubble curve that Tarek derived for us here, this is what shape of a function? It's a straight line. It's a linear function. So the bubble curve is a straight line in an ideal Raoult's law system. The dew is some sort of a radical function, right? So that's why it has kind of a radically function shaped curve. So, again, this is like my first time ever seeing a phase diagram. And I'm not joking, I do this every time I look at a phase diagram. PXY, high pressure, liquid phase, this is the bubble curve. So what I will do, if I have an ideal or a non-ideal system for a liquid phase mixture, I have, let's say, some arbitrary composition. So I know in this case, Z of A is equal to X of A, which allows me to solve for activity coefficient of A, activity coefficient of B, right? Because I have an activity coefficient model. If I don't, then I'm in trouble. If I don't have an activity coefficient model, I'm going to go into the lab and I'm going to measure the bubble curve. Then I'm going to fit it with an activity coefficient model so it all agrees. That's how we get this thermodata. If you have access to vapor-liquid equilibrium, it makes fluid phase equilibrium calculations so much easier. So for the problem is, modern engineering research for thermodynamics is for systems that you cannot trivially do vapor-liquid or liquid-liquid systems. So I do a lot of work in a material called asphaltenes. Asphaltenes will thermally decompose before they vaporize. So we don't have really good VLE data, which means we can't benchmark our activity coefficient models, which means it's a shot in the dark. We don't know what's going on. So it's a lot of guess and check work. So what we do, if we want to calculate the bubble curve, the dew curve for a non-ideal system, the bubble curve is straightforward. We just take our equation for our modified Raoult's law with an activity coefficient model. It's just plug and chug. We assume a value for the composition, we insert that into our activity coefficient model, and we know our pure species vapor pressures or fugacities if we're not making that assumption, right? If we're not assuming low pressure vapor liquid equilibrium. So this is an explicit equation, not a pleasant equation, but it's explicit. So I can generate this line exactly. Then, how do I cheat the system and get my dew curve? What is the relationship between this point, X of A, and this point, which corresponds to the mole fraction of A in the vapor phase? What is an equation that relates those two? Yeah, it's modified Raoult's law. So in this case here, the mole fraction of species A is just equal to that. So I always go from the liquid to the vapor, and then I repeat this calculation a whole bunch of times. Connect the dots, and I've got my dew curve for a non-ideal vapor-liquid equilibrium. This is non-ideal in the liquid phase. So in this equation, last thing before we go, what are the main assumptions that go into this equation? Ideal gas mixture.
Ideal liquid mixture?
No. That's the one assumption that does not go into this equation. This is a non-ideal liquid mixture. And then what's the last assumption that goes into this? Low pressure, meaning we can neglect the Poynting correction, right? That the pure species fugacity is equal to the saturation pressure. So all of vapor-liquid equilibrium is just manipulation of these like 4 or 5 equations that we put on the board. But there's a lot of ways we can manipulate it, right? All right, good luck on, I guess, the fluids study and practice. And see you all on Friday, or maybe some of you on Friday, I guess. I don't know, see you guys.
So it's not ideal because there's the activity coefficient.
Exactly. So that's the one assumption that it's not.